Okay, so we are looking at the first section of this course, and after this section, hopefully you guys will be able to find the average rate of change of a function over an interval. And I'm just reading through these course objectives in front of you. So also, I hope you will be able to find the equation of a tangent line at a given point. So don't worry if you don't know what those things are yet, because we're going to talk about it. You should be able to solve applications, solving rates of change, and you should be able to find the average rate of change of a function and find the limit of the average rate of the change over a function. So that could kind of might not understand what any of that meant, but hopefully once we finish, we can go back and hopefully you'll recall and understand what those things are. So just kind of about what we're going to be talking about today. And let me just kind of quickly read through this. You don't need to take notes on this, but let's just do this. So in this section that we're covering, we're going to look at two fairly important problems with the study of calculus. Okay, so this is going to get us into that topic of calculus. So there's two reasons for looking at these problems right now. The first, both of these problems that will lead us into the study of limits. So limits is a really important concept of calculus, and which is the topic of this first chapter after all. So this first chapter, if you didn't know, is called Limits and Continuity. So it will lead us into what a limit is. Looking at these problems here will allow us to start to understand just what a limit is and what it can tell us about a function. So some of you might have some previous knowledge of calculus and know what a limit is. And then secondly, the rate of change problems, that's where we're going to start looking at one of the most important concepts, which we're going to encounter next chapter of this course, which is the derivative. So we'll talk more about that later on. Okay. So in fact, it's probably one of the most important concepts that you'll encounter in the whole course, which is derivative. So looking at it now will give us a start of thinking about it from the very beginning. Okay, question for you guys. What does it mean to find the average rate of change of a function? So just I'm going to give you a second to think about that. Okay, so you guys, it gave some great feedback. The thing was paused, the video was paused, about finding the slope of a graph or finding the average slope of the graph within a graph. When we're finding the average rate of change of the function, actually, before I even go into that. So let's say I just looked it up. It is 24.7 miles from my house to the Yuba College campus. So we have 24.7 miles. And I know that when I drive to campus from my home, that it pretty much takes me 35 minutes from my getting in my car from my door to the campus, getting out of my car. So this is 35 minutes. So could I find the average rate of change of, can I figure out how fast I was going? First of all, how about that? So how fast? Or was I traveling or am I traveling? Could you tell me how fast I was traveling? Could we figure that out? When we've worked back in algebra, our distance problems, right? Distance equals rate times time. So I could use this formula, distance equals rate times time. So my distance is 24.7 miles, right? is equal to my rate. I'm trying to figure out how fast I'm going times time. I want my rate to be miles per hour because that's just how we look at our speedometer, right? Miles per hour. And so I want to first convert my 35 minutes into, let's convert this to hours. Well, I know that there's 60 minutes in an hour. And so 35 minutes over 60 minutes. So I'm just going to reduce this a little bit. I notice they're both divisible by 5. 5 goes into 35 7 times, and 5 goes into 60 12 times. So I know my time here is 7/12. Okay, so I want to solve for my rate. It's a linear equation. So when we're solving for equations, it's important to see what type of equation it is, because that kind of clues you in how you go about to solve the equation. So it's linear. That means I want to get the variable by itself, get everything else on the other side. All I have to do right now is get rid of that 7/12 in front of my r, and I can do that by multiplying both sides by the reciprocal, or divide both sides by 7/12. It's easier to multiply by the reciprocal though. And so I'm going to multiply both sides by 12/7. So just to save time, I'm just going to throw this into the calculator. So 12 times 24.7, all divided by 7. This is giving me approximately, so I'm going to approximate it. So this curly equal sign, my rate is approximately 42 miles per hour. So my question for you is, was I going 42 miles per hour that whole time?
No, it was the average speed throughout your entire trip.
So that's my average speed. And so when we're finding that average rate of change, we're looking at that, in this case, the average speed that I was going, if I had summed up, you know, how fast I was going at that time, etc. Okay, so this was my average rate of change. So average rate of change, we think of it as a slope between 2 points. So maybe let's say that I have some function here. And I wanted to find, I'm just going to draw, it's just random picture of some function here. Let's say that I have some value in here. Oh, I'm sorry. That this is my x value is a here, and my x value of b here. And if I wanted to find my average rate of change, I'm finding the slope between these 2 points. I'm gonna see if I can do this. So the average rate of change from x equals a to x equals b on f of x, we can get by doing the following. Let me give myself a little more room possible. Oops, maybe that was not good. Let me just go back. There we go. Well, that's just the slope, right? And so recall, and I'm just going to write this. This is the slope of a line. Remember, the slope of the line is the change in y all over the change in x. Another way to write that mathematically, that change in y is by this triangle. So triangle y over triangle x. So just real quick, recall that we can write points. If my x value is a, I could put my y value there, but I really don't know what that is, right? I can call that y value f of a. So that notation there, f comma a. And here, this is going to be my f of b value. So I have a point when x is b, my y value, if I plug in b wherever I see an x in that function, I can write it as f of b. So my change in my y value, so it really doesn't matter which way you go. I'm going to look at choosing f of b as my first y value. So my first y value, f of b minus f of a, all over my change in my x value. So the change in my x value is my x value is b minus a. So that's giving me the average rate of change. If it would be impossible to do it, but basically if we took every x value between x equals a and x equals b, and we found out what that y value was, and we averaged them all up, we would get back what that average rate of change is. So this line that I drew between those 2 points is an important line, and that is called the secant line. So a secant line, is the line through 2 points on a function with a, okay, that's just fine. Okay, so average rate of change is something that we've dealt with before in the past. The question though is, so I got the average rate of speed I travel to work is 42 miles per hour, but I know for sure that that's not the case. There's times I have to be going 25 miles per hour, I will be getting a ticket, or, and because I'm in my neighborhood, or there's times I am, sorry, putting the pedal to the metal to fly down a Hamilton Smartsville. Anyways, so what if I wanted to know an exact speed at an exact time? So I wanted to know, okay, at 10 minutes after I left home, I want to know what my speed is at that time. And that's where calculus comes into play. We call that rate of change at a specific time and at an exact time, we call that an instantaneous rate of change. And so we're going to be using that concept, that instantaneous rate of change, to bring us into what a tangent line is. Okay, so we have our picture here of some function f of x and finding the average rate of change between 2 points on that function. But like I said, maybe I want to know what's happening at a specific time. So let's look at, I'm going to just redraw my picture. And let's look at maybe looking at how can we find the instantaneous rate of change at one x value? What is that slope right there? If we were going to try to find out the slope. Before in our mathematical careers, we could only find the slope of a line, but now we're going to learn calculus, and that's going to help us find the slope at any particular point that's defined on a graph. Let me just pause for a second, see if there's any questions. Okay, so again, we have this generic graph or some graph in front of us, and we want to figure out what that instantaneous rate of change is at some value of x. And I just decided to say arbitrarily x equals a. Well, if I took some point that was arbitrarily close to x equals a, and I found that rate of change between those 2 points, it could be helpful. So let's say that I just add some value in here of h. So if I add some value of h, just think about this. This length in here is h. So really I can call this x value in here, I can call this x value a plus h. Right, because this length is a plus this length of h gives me this back of a plus h. And so if I did that, right, and I come and I find the slope between those 2 points, and before I do that, I'm wondering, I'm going to save this so I can just copy and paste. Okay, perfect. So if I go here over here and I draw my line, oops. And I draw my line. This line, it gives me kind of an accurate slope of what's happening at this point, x equals a, but I think that I can find even a better estimate if I shrink that value of h. So let's say instead, we just come out here. Let me just go ahead and recopy this. Let's say instead, I don't make h go over that far. And I even make that h smaller. I make that h value right there. I don't like that. I make that h value even smaller than right here. So maybe right in here. And so let's make h get closer to 0. I'm making that distance between my a and that value I'm adding to it closer to 0. And so now if I look at what a plus h is, so I'm up here, where's my y value? This is my f of a value. And I want to find the slope between those 2 lines. And if I look at it, sorry. As I look at it, notice that that line here, the slope right in here, it's getting me, I think, a little better estimate of what the slope is at this particular point. And so really what I'm going to be doing is I'm going to keep shrinking that distance between the point that I'm choosing that is next to A. And as I do that, the closer and closer I'm going to get to what the instantaneous rate of change is at that particular value. So notice we have 2 points here. We have the point when x was a, so I'm going to put that there. My y value is f of a. Sorry, I like my things thicker when I write. And I have this other point in here. I'm adding some small value to my x equals a. So a plus h, my y value is f of a plus h. And so if I want to find the average rate of change So my change in my y value. So I'm going to write f of a plus h minus f of a all over my change in my x value. So I started with my y value when x was a plus h. I got to do the same thing in the denominator. So a plus h minus the x value would be a here. And so I'm going to simplify this a little bit. I can't distribute that f. That's not what that's saying. That's just saying my x value is a plus h, and I'm plugging that back in wherever I see an x in my function. So I'm going to keep my numerator the same, f of a plus h minus f of a all over. Well, notice my denominator, I have a couple like terms in there. That a minus a, those cancel out, and I'm just all over h. And so I'm going to write this so that I'm specifying that I want that distance, that h value, to get smaller and smaller. I want that distance to be infinitesimally small. I want it so close to 0. And so we're going to write this as LIM. And then underneath, you're going to see an h with an arrow to 0. Of the following. So f of a plus h minus f of a all over h. So that h going to 0 again is just saying that distance between those two x values is going to 0. So this actually is part of the formal definition of derivatives, but we'll learn that later. And we'll talk more about this notation a little later too. This hopefully looks a little bit familiar to you. I don't know if you guys remember back in algebra, the difference quotient. And if you had me for algebra, I'm sure I went into the fact of where this is going to bring us in calculus. But the difference quotient, recall, if you have f of x, is f of x plus h minus f of x all over h. The other thing I just kind of want to state right now, and we're going to get more into detail about this, is that this is giving us the instantaneous rate of change. At x equals a. So if we can find out what that instantaneous rate of change, so that's that slope at x equals a, and we can find the equation of the line that has that slope through x equals a on the function, that is what brings us to what the tangent line is. So let me come back up here and paste. Okay, so if I wanted to look at this, and I wanted to find the tangent line or equation of the tangent line, what I'm doing is I'm getting that instantaneous rate of change at that particular value, x. I can't draw straight lines, that's why I'm using this tool. So this is gonna be the, this is the tangent line. Let's make that darker. And this has the slope is the instantaneous rate of change. And that's spelling right, instantaneous rate of change. Okay. Okay, so you're going to be throughout the semester asked to find equations of a line. So find the equation of the tangent line, find the equation of the secant line. And so you got to recall how to find equations of the line. So recall, so kind of going back to algebra really quick, finding equations of lines. There's two things that you need when you're finding equations of a line. You need a point on the line, and you need the slope. And if you're not given those two things, you're always going to be able to find those two things. Right away, you can find a point on the graph by, if you're given the function, just going back in and plugging in what that x value is, right? Wherever you see it in that function, and that will spit out your y value. So you got a point there. And then we can find the instantaneous rate of change, or we can find the slope by a couple different ways, using the instantaneous rate of change if we're trying to find it for the equation of the tangent line, or we can use the average rate of change if we're looking just at the equation of a secant line. Okay, so let's go over a couple of examples. I'm just going to grab a couple from your textbook. And as I'm doing that, I'm going to pause, and if you have any questions or need any clarifications so far, let me know. Okay, so our next example, we're looking, or our first example, really, I was just kind of explaining concepts before. You have r of theta, that's equal to the square root of the quantity 4 theta plus 1. And we're trying to find that average rate of change over the interval of 0, 2. So I want to look, I need to find my points. And so I can find my points. So I can look at what is r of 0. And so what I want to do is wherever I see a theta in my function, I tend to put a parentheses there at first, and then I go back in and plug in what I'm going to do. So I have square root 4, I see a theta, so put a parentheses plus 1. And inside that parentheses, I'm going to plug in what theta is, which is 0. So r of 0, using order of operations to simplify, I have the square root, 4 times 0 is 0, plus 1 is 1. So I have the square root of 1, which is 1. So I know I have a point at 0, 1. Now I want to plug in 2. So I want to look at what's happening, what's r of 2. And so I'm going to go over here, and wherever I see a theta, I'm going to put first a parentheses And then I'm going to go back in and plug in 2 wherever I have that parentheses. So order of operations, simplify underneath the radical first. That's like a parentheses underneath there. Multiplication comes before addition. So 4 times 2 is 8. Then plus that 1 is 9. So I have the square root of 9. And the square root of 9 I know is 3. So I know I have a point on the graph at 2, 3. So the average rate of change is the change in my y value all over the change in my x value. So change in my y value, doesn't matter which point I start with, just be consistent with the top and the bottom. So 1 minus 3 all over 0 minus 2. So 0 minus 3, that's -2 all over -2. So this is giving me a slope of 1. So if part 2, or part B of this problem said, find the equation of the secant line, on that interval 0, 2. Well, we already have the slope of that line. This is what our m value is. So we have our slope of the line is 1. And we actually have a point. We actually have 2 points, right, on the line. And it doesn't matter which point you choose. We're going to get the same equation. So just choose one. And I see that this point's actually going to be so much easier because that is my y-intercept. So recall, and it's easiest or helpful when you write your equations in slope-intercept form, that y equals mx plus b form. So I know my slope, y is equal to 1 times x. I wouldn't put my 1 in front of the x, plus b. Well, my y-intercept, when x is 0, my y value is 1. So this is plus 1. And so let's look at one more thing here. Let's say we wanted, actually, I'm lying. Let's look at 2 more things for this question. Let's say we wanted to figure out what the instantaneous rate of change was at x equals 0. Let's find the instantaneous. When x equals 0. Okay, so what we want to do here, and I'm just going to kind of put this formula that I had written up there before. We're looking at the limit, which we denote as LIM, h with an arrow to 0 as h goes to 0, f of a plus h minus f of a all over h. Okay, so our a value in this case, this is what we're trying to find, the instantaneous rate of change at what value. And in our case, my a value is equal to 0. So what I want to do then is I want to go back in here, and wherever I see an a in this function or in this formula, I'm going to go back in there and I'm going to plug in 0. So if I looked at the instantaneous rate of change when x was 2, in that case a would have been 2, and I plug in 2 there. So I'm just going to recopy this down. Limit h goes to 0 of f of 0 plus h is just h, right? Minus f of 0 all over h. I made a little mistake in the fact that we were having our function was theta and not x. So technically, we probably should write that as theta. The other notation that I noticed that I did wrong was my function, that name was r, not f. So in our case, maybe I should do that down here. So let's do that theta here. Actually, that's still h, sorry. Okay, and in our case, a is 0, or we let theta equals 0. Oops, and I said that was r. So let me go back up and kind of grab that equation. Notice that this is our equation. Our theta is 4 theta plus 1. Down here and do that. So if I do this in pieces and I look at what is r of h, all that's telling me to do, right, is to go into my function, and wherever I see a theta, I'm going to put a parentheses and then go back and replace it with what I'm substituting in. I'm not substituting in a number in this case, I'm substituting in a number, a variable h. So I'm just going to simplify that. That's the same thing as 4h square root of 4h plus 1. And then I want to look at, that's just this piece. I want to look at what is r of 0. So let's just plug it in. Let's figure out what r of 0 is. Well, we already actually did that work above, right? We found that r of 0 we got back was 1. So r of 0 is 1. And so let's go back in. Let's replace what we just found. So I have the limit as h is going to 0 of r of h, which we just found was the square root of 4h plus 1, minus r sub 0, which we just found was 1, all over h. Sorry. So I need to find the instantaneous rate of change here. I'm actually going to have a problem if I go in, and we're going to talk about this later when we actually look at how to find limits of an algebraic expression. What happens if we go and we do direct substitution, we get 0 over 0. It's an indeterminate form and it doesn't tell us anything. Okay, but this is what we can do, because I want to find the instantaneous rate of change. And this is, I'm going to teach you guys how to use some technology that's going to be helpful, especially for this piece. Let's call our function here. I'm going to call it f of x. So instead of having an h in there, I could call it f of h if you want to. I'm going to call it the square root of 4x plus 1 minus 1 all over x. And I want to go in and I want to find points. We want to find the slope of 2 points close. In our case, our a value or theta value of theta equals, or in our case that we're saying it right now, sorry, x equals 0. So if I went in here and I plugged in 0, I would have a problem, right? This gives me the square root of 1 minus 1 all over 0, which is 0 over 0. Let me actually think about this. Oops, and I'm noticing I'm out of time. So let's just pause for a sec. So I'm actually gonna leave you guys at a cliffhanger. You gotta wait until tomorrow, or maybe do some research yourself to see what to do, of how to finish this problem. We want to find that instantaneous rate of change at theta equals 0. So just so that you know, we just started that first section that we're covering in your textbook, and for this course, that's 2.1 in your textbook. So we haven't finished doing 2.1. We'll finish that off hopefully tomorrow and start in on 2.2. But I will start class coming in and continuing going over this problem.